you all for being here. So, yeah, I'm really excited to share our work on optimizing reliability and sign-off for 2 nanometer mobile SoCs. So, these are my co-authors, Sandhya, Matthew, Simon, and Amit. So, let's get started and go over the overview first. So, yeah, to understand why we developed this new methodology, we must first look at the shifting landscapes of the mobile SoCs. Like, as we transition to the lower tech nodes, the adoption of gate-all-around architectures or nanosheet architectures have introduced massive reliability hurdles like EM, etc., compared to other tech nodes like FinFETs, 7 nanometer, etc. So as we pack more transistors closer together and all, the power density increases, the self-heating also increases, causing EM-related failures. So imagine we trying to open an app in our phone and it doesn't get open due to functionality issues because of EM failures, right? So we wouldn't want that to happen. And so in order to tackle these new challenges, we must look at our methodology and execution processes to identify and fix only critical high-risk violations without over-designing our chips and not costing huge amount of human and machine resources like days of runtime, as we know that to run full chip level it requires terabytes of memories and days of runtime, etc. So in our traditional or conventional EM analysis, we basically analyze all the segments or interconnects as a separate single entity where we don't care about the surrounding environmental conditions or temperature, etc. Where we assume some constant value of temperature or some um, conditions and do the analysis, which is not realistic in when we get a silicon chip back because everything is will not be at a single particular value. So there is some pessimism involved in our flow or analysis. So our move flow basically handles or filters out this pessimism, identifies the high risk violations, and saves everyone's times and resources. We'll just deep dive into that flow in the next slide. So this is our main idea where we have three stages here. The first is context-aware EM analysis. So in this, like as I mentioned earlier, we consider all the segments as a single entity and do the analysis, right? So in this context-aware, we unify all the power signal metal segments into a single analysis set and perform the analysis. So here basically the tool identifies the nearby cool wires based on the current flow, etc., and provides some relaxation, which replicates the real silicon behavior. So, and in the second stage we have thermal analysis. So instead of assuming some constant temperature value, the tool actually calculates the heating that a wire can dissipate based on the current flow for a given scenario and activity, and recalculates the EM limit here, and then does the analysis. So, and in third stage we have SEB, which is statistical EM budgeting or fit analysis. Here, as we see in this equation, uh, so this is the fit equation. Basically, the tool calculates the fit of a particular segment, which is nothing but the failure in time. Um, okay, so here the temperature calculated in the thermal analysis is taken as an input, and as we know Black's equation, it recomputes the mean time to failure based on the temperature calculated here, and it substitutes that in this equation. And then the SDC here is the EM percentage that we calculate in the context-aware flow, and LT is the lifetime. So based on these parameters, it calculates fit value for each and every interconnect, and higher the fit value, higher the failure rate. So so for a full SOC level, we'll have one particular chip budget, which I'll explain in the next slide. So if we violate this budget, we have to fix those violations, and if we are within that budget, we can safely waive those DC, RMS, and PG and signal EM violations. So here the important factor is this R, where this is the relaxation factor that Foundry provides us in our tech file, where we multiply with the EM limit. So Based on the foundry silicon testing feedback considerations, they provide us this relaxation factor, which varies for different metal segments based on the layer, etc. And since this is silicon correlated factor, we include this in the fit calibration, which gives us the realistic fit value. And yeah, this is the flow inclusions and exclusions where based on the three stages that we discussed, since we are modeling the long-term reliability effects, which is DC based on the RMS heating within the wire, etc., we can safely waive power and signal DC and RMS EM violations. But we will not be able to waive peak EM violations because those cause instantaneous failures. It does not relate to the lifetime reliability factors. And as we discussed earlier, there are three stages. The first is context-aware EM analysis. So here in traditional flow, we do isolated PG and signal EM RMS analysis, which has unrealistic EM limit because we assume some constant temperature for all the segments around each of the wire and around each and every wire. So in this context-aware, we basically combine both the segments into a single unified set. As we can see here, suppose there is a segment here. From the foundry tech file, we'll have this particular EM check zone that the tool calculates. So here we can see that the wire is orange. This means that this wire is a bit cooler compared to this wire. So what the tool does is, based on the EM percentage of the neighboring wires, like if there are cooled wires nearby, it considers, because it acts as a heat sink for this aggressor, it considers that impact and derives a relaxation factor from the tech file and multiplies that relaxation factor to the EM limit. So as the EM limit increases, the EM percentage decreases, which is a realistic scenario. So post this context aware, we'll have the realistic EM analysis and it returns the EM percentage for both PG and signal. And coming to the second stage, which is thermal impact. So earlier I mentioned that we are assuming some constant temperature for all the segments, suppose say 10C or 20C. So in this thermal analysis, the tool calculates the cell heat, which consists of three different components. So Joule heating is nothing but the heating caused by the wire because of the current flowing within the wire. And instance to wire coupling is when an instance or the transistor consumes some amount of power, it dissipates the heat. And some amount of heat will be coupled to the metal layers. The lower metal layers will have high impact and the top metal layers will have less impact. So that coupling factor will be considered here. And wire-to-wire coupling is the heating coupling impact between the wires. So upon adding all these three segments, we get the self-heating. And we add this self-heat to the ambient temperature of the SoC, like 80 or if the SoC temperature is 80 or 85C. And if my self-heating of a particular wire is 10C, then the total is 95C, etc. So in our traditional analysis, we used to have this fixed T final value. But in this thermal analysis, we'll be having variable T final values based on the local power density, etc. for different segments. And based on this new T final, the tool calculates the EM limit because in the tech file we'll have different reading factors for different temperatures. And in post thermal analysis, we'll have a new DC EM limit, which is realistic. Coming to the third stage, the fit sign-off. So for any product, we'll be having a particular spec. Like suppose if I expect my mobile to work for 5 years or 7 years, based on that, we'll have some chip failure rate. Say if I'm okay with 100 dBPM, that means I'm okay that there are 100 defective parts in a million parts. And all. So based on the chip failure rate and the lifetime spec, we calculate a fit budget based on this equation. So suppose the full chip budget for my mobile SoC is 10, right? I need to ensure that all the interconnects fit values of all the sub-blocks should be less than this final fit value. And coming to the fit budgeting, basically we'll have some compute cores like CPU, GPU, GPU where it operates at high PVT conditions, high performance, high activity, etc. So for those, we'll be allocating a higher fit budget, say like 80% of the fit budget, etc. And for other low priority or low power dense blocks, we'll be allocating a lower fit budget. So ultimately, when we add all the fits, segments of power, signal, etc. for the full chip, it should be within this limit. So yeah, so after doing all these three stages, the output of the flow will gives us the real high risk violations that are actual threat to a silicon which we need to fix. So this is a comparison of the results that we have. So in the first column we have the traditional or conventional EM flow, and in the second column we have the new methodology where I have explained those three stages. So the first two rows are the output of the context aware analysis, which is the stage one that we discussed. So initially we had 5K and 11K violations, and after the detection of cool wires within the check zone width that I have mentioned, basically we got some relaxation, and the violation count reduced by 80% for signal, 47% for PG, and even the magnitude got reduced by half. And coming to this DCM, this is the output of the second stage, which is thermal analysis, where it calculates realistic temperatures for each and every segment, right, instead of assuming some constant value. So here for signal, we got a complete relaxation. And coming to the BG, basically there was some high local hotspot region where the temperature is higher than 10C, which is the default value that we have set, and because of which the EM percentage and the count also increased. So that is the thermal reality story, where if we follow this conventional flow, we'll be missing these new hotspots and be fixing these unnecessary violations which are not actually risky for the silicon. And if you have to fix all these violations, it takes multiple weeks of effort where designers have to fix it, and we have to rerun EM violations and see if it got fixed or not. So it's huge amount of resources and time. And so if we add all these violations, it amounts to 17,100 violations. And instead of that, we'll be having only 135 violations. So these are the violations which have fit greater than 1. So all this will have different fit values for each of these 135 segments. On adding all those, it accounts to 0.5 million. So among the 17K, we need to fix only 135 violations which are really risky in the long term. Example, say 5 years or 7 years. After fixing this 135 violations, on adding all the segments fit, it was under 6, which is within our fit budget. And this fixing of 135 only took 1 week of effort instead of consuming all these weeks of human and resources. So this is how we were able to remove 99% of modeling pessimism in our flow and fix only 0.8% of the real violations which are really high risky for the silicon. So in summary, basically we consider physics over pessimism, where we try to extract what are the real high-risk violations and remove the pessimism in our flow. And we were able to save huge amount of resources, compute and machine-wise, even human resources, etc. And we were able to do a accurate EM analysis. So of all the 3 stages that I've explained, we can, based on the time and project timelines that we have, we can stop at any stage and take the EM violations for the fixes, because each of the stage gives a realistic analysis and the relaxations, etc. So in summary, yeah, that's it. Thank you.